A vector is fundamentally different from anything else that you've probably dealt with in math before. What I mean by that is a vector is not the same as a number. We can't think of a vector that looks like this as having similar properties to a number that looks like this, or any other number for that matter. So how is a vector different from a number? Actually, from now on, I'm just going to call what we used to refer to as numbers scalars. You can just treat scalars as if they're numbers in the traditional sense. So now the question is, how is a vector different from a scalar? Usually you hear that a scalar is a quantity that only has magnitude, but a vector has magnitude and direction. I think this definition is a little bit deficient, so I'll try to make it feel a bit more concrete. Really, in the context of physics, a scalar means a single numerical value can sufficiently describe the scalar completely. But a single numerical value can only sufficiently describe a one-dimensional vector. In order to describe a two-dimensional vector, you need at least two numerical values. In this case, just knowing the x-length and the y-length of the vector is sufficient in giving you the actual vector. Another way of thinking about the same vector in two dimensions is in terms of its magnitude and its direction, where its direction is given by the angle theta it makes with the x-axis. So in two dimensions, if you have two vectors that have the same magnitude and the same direction, then they are the same vector. And this solves the issue that we were grappling with in the previous video in the sense that we now have a complete definition of what makes two vectors in two dimensions the same. They have to have the same magnitude and the same direction. So let's try it out. Imagine we take these two vectors over here and we want to transform the first vector so it's the same as the second vector. Well, in order to do that, we have to take the first vector and scale it up so that it has the same magnitude as the second vector. After that, we have to rotate it so that it has the same direction as the second vector. And now that it has the same magnitude and the same direction as the second vector, it is equivalent to the second vector. Let's try it again. Suppose we want to take the second vector and make it equivalent to the first vector. All we have to do is first give it the same magnitude as the first vector, and then give it the same direction as the first vector, and we now have two equivalent vectors.